Welcome back to class 14. Here is yet another video. This time we're going to do with a steam turbine. Very important thing on board a ship. So let's see, the power generation by a steam turbine. As I mentioned in my story time, on board of the ships, this boiler right here, the explosion, was part of a steam plant, and we usually have a high pressure turbine and a low pressure turbine, and here's like what the layout looks like on an old steamship. And here's where the port boiler is and the starboard boiler. See, this is the left. See, this is the pointy end of the ship is like over here, and here's the blunt end over there, and here's a side view, and you can kind of see where the boilers are right up there. You can also see here's an important heat exchanger called the direct contact heat exchanger, the DC heater. And here's where the turbines are right here, and here's the gears, and here's the shaft, and right here was where I was supposed to be standing when the boiler blew up. Right here by the shaft alley. Here's a little view. You can see there's like this little tiny passageway that you could walk through in between there, between these two boilers right in there. But I thought it was neat. I thought it was a good. This is a drawing from the Patriot State, which used to be, I think, Mass Maritime's school ship. I'm not sure if it still is or not. Anyway, here's looking down on a low pressure turbine, and here's the high pressure turbine, and here's where they're connected to the reduction gear that's connected to the shaft. So this is what a typical steamship engine room looks like. It's all covered in junk and stuff like that. It's old and nasty. But anyway, and there's your D-type boiler and exciting stuff. So anyway, I figured I'd mention, connect the story I told the other day of the boiler exploding. So here's a steam turbine, and here are the conditions on the inlet. Interestingly, they decided to put the potential, the Z, because it's actually true. The turbine is actually sitting on top of a condenser. It's actually built on that way. So the flow is not only going into it's going down into the condenser. And it's being condensed at 15 pascals. So that right there obviously is a vacuum, which is typical for a condenser to go into. And it's got it's partially steam, partially still some partial water as part of it. And here's our velocity. Shouldn't matter. Oh no, actually it did say matter, because it does say to compare these guys together. Okay. So that's one of the reasons why we're here. So it's a 5 megawatt, so 5,000 kilowatt generation, and the inlet temperature is given. We want to determine the work done per unit mass. I don't know why that matters, because I guess because we can get what the flow of the steam is going to be. So that was their whole scheme of the steam. So anyway, we have power of 5,000 kilowatts. That's a lot of kilowatts. Let's take a look at the properties. So get the state properties. Table B.1.3 at, it should be superheated, I hope, 2,000 kilopascals. All right, so 2 megapascals, 2,000 kilopascals. And T1 equal to 400 degrees Celsius. So what do I have to find? I think I only need to find my enthalpy. So 2,000. So I gotta get rid of all those things in here. I can zoom. We want B1.3, and this is at 2,000. Where are you at? 2,000. Boom. And 400, so we have an enthalpy of 3,247.60. 2,000. Did I say 2,000? I meant 3,000. 3,247.6 kilojoules per kilogram. And then for this one, exhaust, we need to go to table, probably based on pressure, because they gave us the pressure. Table B.1.3, and go at P is equal to 15 kilopascals. we'll find out what the saturation temperature is at that. So coming back up to here. Oh, I hate it when that thing comes in. I can never quite find it. Where is it? There it is. All right, so this is the pressure one. We need a low pressure. There you go, 15. Is that right? Yeah, pressure. Enthalpy, sure. And so it's going to be somewhere in, yeah, that's right. Okay, so we need these values right here. So first off, the saturation temperature is 53.97 degrees Celsius. HF is going to be 225.91 kilojoules per kilogram, and HFG is 2,373.14 kilojoules per kilogram. Ta-da, boom. Okay. And so we could find out what H2 is going to be by just putting in our quality here. Plus, here's our quality. I didn't write out the equation, but hopefully you'll remember this is the equation to use for the quality when doing a mix vapor. 2,361.7 kilojoules per kilogram. All right, so we went from this to that. Because they're asking for this thing about delta H to delta K. Okay, we can go ahead and do the delta H now. Delta H is just going to be H1 minus H2, which is going to be 3247.6 minus 2,361.7, or delta H, where'd you go? 885.9 kilojoules per kilogram. I can tell you right away, that's going to be a lot more than the other ones are going to be. All right, so we have the kinetic energy, delta kinetic energy. So you got, that's going to be 1/2 V, I can't remember which one's bigger. It's coming out 180 versus 50, right? So we went from 50 in to 180 out. We could do it on a per mass basis, that's fine. So that's going to be 2 squared minus V1 squared. You have to remember to divide this by 1,000 because we're going to get meters squared per second squared, but to be able to compare to kilojoules per kilogram, that we can work out the math to make sure that is like, oh, they are comparable, but this we need to divide by 1,000. So that's going to end up being 180. Right, so actually, this should be 1 minus 2, so this should be 1 minus 2 if we're going to really compare, right? 1 minus 2. So this really should be 50. Of course, we're going to get a negative number. Spoiler alert. I keep saying it. I don't know if that's not going to be funny anymore. It probably never was funny. But this is funny. That's funny every single time. Every single time. We're going to get a negative 14.95. That's not a lot compared to that. Not I mean, it's some, but not. The potential energy. Once again, that's going to be no mass because we're not going to do that mass. So it's just going to be G Z. Let's go 1 minus G Z2. And so 9.81 times Z1 minus Z2. Z1 was 10, and then it goes down to 6. So we could do that in our heads. It's 4. I almost said spoiler alert again, but I decided not to. Let's see, 0.0. Oh, shut up. 924 kilojoules per kilogram. They're really big fans. They're really big fans. So it's a great bug. It's a great bug. I'm bringing it to class. This is another one too. Oh, I don't like him. Okay. So anyway, we'll compare this change in enthalpy, change in kinetic energy, and change in potential energy. And we say, well, obviously a change in potential energy doesn't matter. If that's 4 meters, that's more than 12 feet. That's math. So that's not all that. It's not a big deal. Now we want to find how much work was done on a per mass basis. So we didn't write out the big equation. Let's write out the big equation. Equals Q dot 1 to 2 minus work 1 to 2. Well, I don't usually do that 1 to 2 thing. Plus change in H dot, oh, M dot. Not change. I didn't say change. Summation. M dot H dot inlet minus total summation of H dot exhaust, outlet, exiting, whatever you want to call it. But you could also go to, on a per mass basis, Q 1 to 2 minus W 1 to 2 plus, and this is all of these things, right? We could go, but there's a change right here. So there's inlet to outlet. We did inlet to outlet on all of these. So we go delta KE, you notice this lowercase, oh, delta H. Delta H plus delta KE plus delta PE. I wish I'd done a delta KE, delta PE. I meant to write that out. Okay. So anyway, they say there's no losses, right? They say they said adiabatic. Yep, adiabatic. So there's no steam, no change in heat, no heat out. Equals negative. This is going to turn out to come up over onto the other side. So you're going to go plus 885.9 plus minus 14.95, and then plus 0.03924. And we get a work done between states 1 and 2 is 871 kilojoules per kilogram. And that was always out. So if you want to find the last part of this, now we can find what the mass flow is going to be by taking that power and dividing it by that work per mass right in there. So 5,000 divided by 871, it's going to be equal to 5.741 kilograms per second. So that was the answer right there. And I think I have one more example. We'll be done with it very soon, but I'm not going to be able to do it. I don't know how many I'll be able to do these in class. I have to plan this out like really well. I really want to do 5 examples, but I don't think I can do 5 examples in 75 minutes. If I'm really disciplined, maybe. I don't know. We'll see.